Hi everyone, welcome back. In the previous videos, we showed how you can design and implement a data science pipeline using Trel. The example that we used was customer lifetime value prediction model. We also looked at data quality validation capabilities of Trel along with A/B testing and experimentation capabilities. In this video, we are going to focus more on MLOps. So based on the functionalities that we have seen so far, it should be pretty clear that Trell offers the ability for model versioning with complete lineage tracking. To get more into MLOps, we will take a look at a situation where we are having a validation failure for our model and see the steps that we take to troubleshoot and recover from this problem. So what has happened is that we have added one more day to this pipeline, which is now at 9/9. And let's take a look at what has happened. So what's happened is for 9/9, we ran features and model, but when we ran predictions, we have a failure. Let's take a look at our incidents, see what's happening. So for 9/9, essentially, we have a validation issue. So let's take a look. So what we are finding is that we had a constraint that's saying that the average predicted customer lifetime value should be between 1,000 and 100,000, and we have a value of 1.3, which is way too low. So clearly there is a concern. But now the problem is this task that failed um, has two inputs. One is new customer data and CLV model. And we don't exactly know which one is the problem. I mean, the R2 score looks okay, but there could be something wrong with the CLV model, and maybe the new customer data is fine. We don't really know. And to debug this, what we are going to do is um, let's take a look at what we say. We're going to run the predictions with the older new customer data and the newer model. And then we are going to comment appropriately. We're going to say that we know the data is correct because it's older, but we're not sure what the model is. And we're going to make a run. We're going to output to a new label just for this troubleshooting. And similarly, we're going to run the newer data and older model and to investigate which actually runs through, and again outputting to the same label. They are not going to overlap because we are actually having different dates for these runs. This one is 9/8. This matches the data itself, not the model. So I'm going to copy this and going to get to a clean terminal and run this. So we have started two tasks. Let's take a look at what happens. Okay, so we see that one of them has succeeded and one of them has failed. Let's take a look at um, what actually happened. So we see that uh, the one that we were running for 9/8 with the correct data and broken model has questionably broken model has passed, but the one we were worried about the data, the newer data, that one has actually failed. So clearly the culprit is the new customer data, and which is the case. This one has a problem. So we can replace this with the correct one to resolve this issue. So let's see. So what we're going to do is replace 9/9 with a fixed data set. And so that is what is now in the catalog. And we are going to be running CLV predictions for 9/9. And we're going to make a comment after fixing new customer data. So let's take a look. So this is what we have right here. And the everything that we can do on the UI, we can do on the terminal as well. And we get the same task report in the terminal. And it seems like everything run through and we're good to go. Cool, cool. Another MLOps step, that common activity that we want to, well, maybe not necessarily MLOps, but experimentation, data science experimentation related to models, is parameter sweep. So, like I said, we would Trel does not support, or Trel does not help visualize and track parameter sweeps that is being done through something like scikit-learn, but you can do a level of parameter sweeping directly through Trel. So let's take a look at how that actually works. We have in our and this is the one we have in production right now. So we have in our notebook these parameters, I and D, and these are iteration and depth. By default, they are set to 1 and 4, and that doesn't look like a very good number. So let's just find out if when we change this number, what does it actually produce in terms of model metrics. So yeah, we are going to run a sweep. We're going to make multiple runs of CLV.model and see what outcome we get with whenever we change the parameters. And here's how we can actually do that. So try to execute CLV model and 99 output to CLV model iterations I1 D2. So we make a label just for a specific set of value, which is I1 and D2. And then we make a comment as well saying that this is the parameter that we're using. And when this produces the results, it will go to this label, and that is how we know what are the parameters, whether we are using the comment or the label, we will know. So what has happened immediately is that this has failed, and this we can investigate while the rest of the values run. Model validation failed. So the task failed because of model metrics validation. If you take a look at it, what we find is that the R2 value is so low that it didn't even hit a minimum threshold for R2. So this model is not acceptable even with warnings. This will proceed for some time, so we will skip ahead in time and directly see the results. We're back. Let's take a look at what we have. So if you go to tasks and take a look, we can see the failed task, and the remaining ones were successful, starting from I is equal to 1, D is equal to 3, all the way to I4, D5. So the best way to see the outcome of this is to look at the data sets that is corresponding to model metrics, and it would give you the right picture. So we ran everything from I1 D3 all the way to I4 D5, and we can see how the R2 score metric is actually improving over time. So it seems like we kind of hit a limit at I4, probably around I2 D5. So we'll just split the difference and pick I3 D5 as the one that we really want to adopt, because it's definitely much better than I1 D4. So going forward, that is what we want to put in production. But instead of doing that immediately, we will do it as part of the next demo. Okay, so let's just go back to our slide and take a look. So one of the capabilities that is really desirable for MLOps is automated model retraining based on data drift or performance degradation. So as I mentioned earlier, we're not going to look at data drift specifically, because that is something that you have to compute using custom code or SageMaker or MLflow, and use that to kind of trigger a performance degradation uh, using data quality rules. So we'll take a look at performance degradation based on R2 rather than data drift, and see how we would do that. So for this, we are going to define a job called model dynamic. So model dynamic has a notebook as well. So let's briefly take a look. Okay, it's not a problem. All right. So what happens here is that we have now added another parameter, performance threshold, which is at zero point 0.8. So what that basically means is if the model is performing at least zero point 0.8 R2, we don't have to redo the model. But if the model falls behind zero point 0.8, then we do want to rebuild the model. Okay. So the inputs, another change is that instead of this model building job taking only the features, it now also takes the yesterday's model. Okay. And of course, the rest of it is same. The schema version is still there. Now, the change that is going to happen for us is here. So the first thing we're going to do, one thing we have added is we're going to load the yesterday's model, and we are going to evaluate the yesterday's model on um, our latest data that we got. So we apply the test data to the yesterday's model and see what score are we getting. And what we find is that if the if the R square R2 score is higher than the performance threshold, then we can just use the yesterday's model. Otherwise, we'll go ahead and not use the yesterday's model and build another one. So if we're not using the yesterday's model, we're going to have build it, and then everything is sort of normal. The only change here is when we come to the comment, right? We're going to add whether or not we actually uh, um, recomputed the model or not, rebuild the model or not, so that we can see this clearly in the UI. So that's pretty much it. Let's go ahead and what would have happened so far is we have created 910. And let's also take a look at the registration for this job. So we have a different scheduler called periodic for this because this is no longer single instance. Single instance means all the inputs have the same instance. But here, features has one date and model has the previous date. And that is covered by periodic, which follows a pattern where one is updating the other. So it's as if features is updating model. That is just the pattern. We're not exactly updating the model using features, but since the pattern is the same, it works the same. We still have the schema version migration logic for model, and we can go ahead. Let's see. So we will trigger model dot CLV dot model dynamic, and we can see the outcome of the run that actually happens. So when we trigger the job, we have this model.dynamic run, which is running for 910, but is passing 99 model, which has a 0.75 performance. And we will see if it should find that this is not adequate and it should build a new model. So let's just wait and see what happens. So what we can see is that when we refresh this, that this has completed and it has actually chosen to create a new model. And the new model is using the parameters that, oh yeah, there's the other change was that the parameters here have been updated to be 3 and 5 rather than 1 and 4 it was before. So the new parameter was used 3 and 5, and we have the better score that we're looking for. Great. And because that happened, now predictions also has followed, and we have everything working out. Note that one of the reasons why CLV.model dynamic ran, but model did not run is that the script actually disabled CLV.model to manual only, and CLV model.dynamic is now what is in production and scheduled. Okay, so now what we will do is we will add one more day, and we can observe whether that makes any difference. So let's wait for it. Okay, so model dynamic just completed. So let's again take a look at what's happened. So the input was new model the the new model that was computed for 910 with 0.88. And what we find is that in this time, it actually chose to use the same one, and it still has 0.88 as the score. And this score is constantly getting reevaluated from the CLV.features. They are the same because this the data in CLV.features is the same for 911, 910, 99. It's pretty much the same. So that's why these scores are practically identical, even though they are getting recomputed. Great. So let's get back to the slides and take a look at um, a few more points. What we see here is that we are able to successfully monitor the model performance across multiple versions. And next, what we want to take a look at is you know the the trail of model deployments to production, right? For this, Trel offers the ability to, you can write a job called model.deploy, clv.model.deploy, and that job is now responsible for pushing the model to production. There can be some safeguards in this job, and we'll take a look at that briefly. And I also want to mention that this deployment job can deploy either to some internal data store or external model registries such as SageMaker model registries or MLflow model registries. All right, so let's take a look at what special considerations are there for this job. Okay, so if you take a look at the new job that got created, it's a pretty simple schedule, single instance. We're using the model, but the main thing to note is that where we are actually deploying, there is an alt URI in it. So the alt URI basically overrides Trell's mechanism of coming up with new URIs for every output. And now all CLV.model deploy is actually going to output to the exact same location. So what is the impact of this? So let's take a look at the notebook to better understand what's going on. So we again start with our standard imports, and already we can see some difference. We get the input URI, we get the output entry and the output URI. And the first thing that we do is compute a lock URI, which removes the trailing slash at the end of output URI and adds a dot lock suffix. So this is the file, this lock URI. And we also are going to parse the additional arguments and additional argument CLI for a force parameter. Okay, so the one logic that we want to get right in a deploy script is that we want to keep deployments advancing in date. So if we have 9.9 deployed or 9.10 deployed, if you try to deploy 9.9 after that, it should fail because 9.9 is older than 9.10. This is also a safeguard against the Trell jobs ability to run in parallel and the tendency to run in parallel a lot, right? So if the deploy job runs in parallel across 9.1 to 9.10, then we would be dumping 10 different models to the model registry at the right time, all of them fighting to be the final model. And maybe the model registry, some model registries can sort it out, but most deployment endpoints will not be able to handle either the data transfer or carefully finalizing which is the one that should be in production. So to prevent this, we are going to bake in some locking mechanisms into the job itself. And the first step was to actually ensure that all the jobs have the same output location, and thus the log file for all the jobs will be the same as well. Now that we have a log file, what the notebook is going to do is um, read the contents of the output. Actually, yes, excuse me. Okay, so read the contents of the output, get the current deploy timestamp from the output location. So the output location, uh, would basically have a Parquet file which has one column that has the current deployed timestamp. Okay, so then what happens is the notebook decides whether or not it should deploy. So it should deploy if it is forced to deploy, or if the current deployed timestamp is none, or if the new model timestamp, which is coming from the instance timestamp string of the model from the args, is actually higher than the current deployed timestamp. And once it decides it should deploy, then it's just going to go ahead and do it. But if it doesn't, it decides it shouldn't deploy, it's going to raise an exception and die. Okay, so once it's going to deploy, we are going to um, try to acquire a lock, and we do that by putting a text called locked in the lock URI. And if you are able to successfully do that, I apologize. Let me remove these older functions from the notebook and use the one from the library. So args comma lock URI, and the same for later release lock as well. And we're going to get these functions from Trel dev. All right. With the changes to the notebook, let's take a look at how we can actually run this job and see if the deployments follow the processes, the principles that we spoke of. Okay, so we come to model.deploy and we want to execute. We'll start by executing for 910 and wait for it to complete. This shouldn't take too long because this is a relatively quick job. We'll just wait for it a bit and see. Okay, so as we take a look at this, the deployment for 910 is completed. Now let's try deployment for 99. This should fail due to the lock. Excuse me, this should fail due to the timestamp being older. So let's take a quick look at the actual run, and what we see is that that is exactly the reason why this one has failed. Now let's execute again for 911, and this should go through. We'll refresh this and we can see that yes, this is completed. So going back to our slides, we can see that we have a clear audit trail of model updates. And if we want to override or revert some of the changes that we made to, and with an older model, then we simply has to pass minus minus force to the notebook as an additional argument, and it'll be able to update with an older model as well. And all these deployments only happen through this clv.model.deploy job. So all model updates and approvals are clearly visible through the list of tasks that it got executed. It's important to clarify that there are some advanced model features that are not covered by Trel, because Trel is fundamentally not responsible for storing or serving your models. So, model serving features such as A/B testing of models and canary deployments are not supported, but will be supported by the model registry that you're pushing your model to multi-model ensemble will also be taken care of by the model registry. Automated model compression, if you are doing any sort of edge deployment, and specialized model documentation features, these are also something that you can depend on for depend the integrated registry. Uh, let's say use the model registry for. Next, let's briefly take a look at some of the collaborative capabilities of Trel. Some of the functionality that is covered by Trel is, as you can see, experiment sharing. So, since all the experiment is being done in a dedicated label, simply communicating the label to your colleague would be more than enough for him to or her to take a look at the trail interface, filter for that label in the for the data sets, and see exactly what work has been done. This also offers a strong form of single source of truth, because your data assets are organized by data identities, and when anybody wants to refer to a specific identity in terms of an experiment, they can directly find out what is the current path that is corresponding to that identity through the catalog. And there would not be a case of um, an older path being replaced by a newer path, but other pipelines still continuing to use the older path. Um, Whatever is currently in the catalog is what is going to be used by all operating Trell jobs. In addition, there are other shareable data artifacts that can be reused by um, your team members. This, of course, the feature store, but you can think of it as a data set. Data quality, rule definitions can be shared. Um, Data can be the overall, a data set or a sequence of data sets with the same data set class can be reused by a team member by using a formula that is which has one of the inputs, something that is being produced by a colleague. And lastly, it is also possible in Shell to trigger others transformations by using the catalog. So we can take a look at this briefly by seeing this diagram. So this is your identity space consisting of one set of dataset classes. And here there are a couple of dataset classes, one of which is an input to a pipeline that is belonging to a colleague, and this one is the output of that data transformation pipeline. So to trigger your colleague's data transformation pipeline, you can use one of your jobs to generate the data um, with the dataset class that is corresponding to your colleagues, and the presence of that entry will automatically trigger your colleague's pipeline, and output will be produced, and this output can be used as an input to your pipeline. So when you run this job during automation and this dataset created, this pipeline will run, and the resulting data set will be used by your pipeline seamlessly without having to learn anything about how is this data set getting transformed to this data set um, on behalf of your colleague, right? So this kind of collaboration and integration of other people's pipelines really boost the ability to leverage the expertise of your colleagues without having to um, communicate that expertise and having to learn that those pipelines and how it works before they can be integrated to your pipeline. Let's take a look at a few demos that are related to this. So what we see here is um, the publishing capabilities of Trell. So we are going to, as a different user, not the user that you're seeing here, publish one of the data sets, new customer data. And let's take a look at what it looks like. So new customer data is now published. So if we filter this, we can see all the published data sets. So if we want to subscribe to this data set, if this is a data set that is interesting to us and we want to use it in our pipeline, it is advisable to subscribe to this data set. And if we do so, it takes us to this interface which gives us the uh, SLA specification of this data. So this is when the data will be made available uh, in relation to the instance timestamp. And this is when, beyond this point, it'll be too late and there'll be no more alerting on top of at this point. So the publishing and subscribing mechanism allows a publisher and a subscriber to communicate, data sets, schema, and SLA specifications, so that if the data violates the SLA specification, the subscriber and the publisher gets alerts. Similarly, I can also publish one of my data sets by first adding an SLA and then publishing it. So I'll go ahead and choose CLV dot features for publishing, and you have to specify a repository that you're publishing at. And then let's say 200, and let's say this also is, let's say 93600. So I'm just going to add 7200 to one day to make sure there's no gaps. And we're going to do demo. We're going to add this SLA. And so now I have added the SLA, and this SLA, this will alert me whenever this data set is falling behind, but this is not published yet. But if I go ahead and click this, now this data set is published, and it'll show up here as a published data set, and others can go ahead and subscribe to this data set, and we will be able to see them when we look at the subscribers list. Okay, next, let's take a look at how we can collaborate on schema. We already know that schema can actually um, be visible, is visible to other people, and we have very clear notion of versions. But these versions is not always something that has to be in production. You can have other versions which don't really aren't really even expected to be in production, but simply as a documentation or intermediate schemas for collaboration and communication with each other, with your colleagues. For example, if you're looking at this feature store, your team members could be developing different sets of features, and you can clarify that by having different set of versions, maybe this naming convention, and in the end you can bring it all together to a new version called 3. But in the during while that happens, you can have this additional versions for communication. So one of the examples that I mentioned was how you can trigger some other pipeline. So let's take a situation where a sales department wants to trigger a data science pipeline by putting some customer information into the data catalog, which will trigger a trigger the prediction job to take that data set, make predictions using our CLV model, and then put it in a way that the sales can pick it back up. Okay, so let's take a look at the configuration for this job. Here again, the configuration or the formula has become somewhat more complicated. So we now switch to a different class called multi-period, and this is a class which allows you to choose this option called prefix label selection. Typically the prefix is null, or prefix is a single value, and label is also a single value. But if the inputs don't have the exact same prefix and label, you can use prefix label selection to specify which prefixes that you want. So what we are going to do is CLV.model is going to remain as a null prefix and a demo label, but new customer data is going to be sales prefix and demo label. So the sales prefix separates this inputs for this job from the regular production inputs, because the regular production new customer data has null for prefix as well. So you can now have two different new customer data for the same date and label and repository. They're just differing in the prefixes. Okay, so with this in place, and the output is also going to be sales prefixed. So these input and output data sets are completely separate from, they are in production, but they are completely separate from the existing production pipeline. Finish this. So now we are going to add a data set with the sales prefix. So this is usually was empty before, but this is where you actually provide the prefix. And let's see what happens. So if you take a look at tasks, what we're going to notice is sales is actually triggered, and the schedule ID also indicates that we are going to be processing a sales prefix, and the output when this completes. Let's just quickly take a look. Prediction runs reasonably fast. Okay, so if you go ahead and refresh this, we can see that yeah, the input and the output both have sales, and these are separate from the other data sets that we have. So if we go ahead and take a look at the data sets, let's go ahead and refresh this once more and take a look at CLV dot predictions. And then we can see here that also the issue was that it is 99. Probably just scroll down a little bit. So for 99, we have here. So new customer data, sales, and CLV predictions for sales as well. Okay, and this is largely the end of the demos that we have. So let's go back to the slides and talk a little bit more about, take a look at the pipeline dependency visualization. Typically, when we think about pipeline dependency visualizations, we are thinking DAGs. But in a department, in the data science department, the work is not really done in one single tag, but a sequence of tags or a number of tags. And the dependency between these tags, the collaboration between these tags typically are lost. But with Trel, because of this formula based automation, all dependency between jobs in Trel is clearly apparent through the formulae. So by looking at the formula, Trell can reconstruct the entire dependency graph or all relationships between jobs and data sets within your entire organization. So let's take a look at what it looks like for the work that we have done so far. So if we go to graph, we can see that we have four different sensors, four input data sets, and we have two different jobs, the CLV features and MPV generating features, which is being used to generate model and model metrics, and model is being used to generate predictions, and model can also be directly deployed. So this entire graph is being inferred from the formula that is being provided to Trell. Okay, so it's important to talk briefly about the capabilities, how we can use the capabilities Trell offers for regulatory compliance. Trell offers three key features that help. So the first is automated enforcement of data access policies. Trel achieves this through its repository system. Repositories control data storage locations, and all jobs and sensors only specify the repository, not the actual path. This abstraction allows for flexible access control. For example, you can have multiple repositories, each with different access controls managed through your cloud platform's native tools like AWS IAM. I had given an example of this earlier with Data Lake and Data Lake PII. Some dataset classes can be restricted to specific repositories, effectively limiting access to certain groups. Imagine in a dataset class called addresses.plain that is restricted to a data lake PII repository, ensuring only authorized personnel can access the sensitive information. Second, Trell provides comprehensive audit trails for data usage and model decisions. Every interaction with your data is meticulously logged, allowing you to trace the lineage of any prediction back to its data source data. Lastly, Trell offers data retention policy management through its lifecycle module. This allows administrators to set complex rules that automatically delete unwanted data identities while preserving critical ones, all managed from a central location. This feature provides both guarantees of data deletion and visibility into the process. These features work together to create a compliance framework that is both robust and flexible, adapting to your specific regulatory needs while integrating seamlessly with your data science workflows. In closing, let's quickly recap some of the advanced data operations that we saw during this presentation. We saw um, schema evolution and validation. This feature allows your data structures to grow and change alongside your business needs, all while maintaining data integrity. We also explored the power of immutable dataset versioning. This approach ensures you have a clear, unaltered history of your data, crucial for reproducibility and auditing. One of Trell's standard features is its unified dependency visualization. We just took a look at that example. We touched on environment specific what if scenarios, allowing you to test changes safely without affecting your production environment. And this capability is a game changer for experimentation and gradual rollouts. Throughout our discussion, we emphasized the importance of historical tracking and auditing. Lastly, we explored how Trell enables efficient parallel executions, allowing you to scale your data operations seamlessly as your needs grow. These advanced features work in concert to create a robust, flexible, and powerful platform for your data science needs. They're designed to address real world challenges you face every day, elevating your data operations to new heights of efficiency and reliability. So, if you want to try out Trell, feel free to sign up at trellcloud.com, spin up a Trell instance, and just like what I had mentioned earlier, just by providing the information for repositories and providing a few credentials, you would be able to build data science pipelines using Trell. Good luck.